Okay, let's start. So as you can see, we are about 5 minutes late. So I'm Italian. This is the Italian style. We are never punctual on anything, okay? But I've been told that I can take 5 minutes from the break. So basically, I'll be late, and you'll be paying the consequences for that, which is yet another Italian thing. Design for testability. Now, I'll start with a short version for you. So if you want to go and do something else, you can do this after this slide. That is, to be tested, the system has to be designed to be tested. This is the core of my talk. But let's expand a bit on it. So design for testability is a concept that was born in the hardware world, okay? Was born in the hardware world because when they were building integrated circuits and things, one of the problems was, how do we test these things now? So the idea was to put some connectors for the only purpose of testing it, okay? So connect your testing infrastructure, set the state of the system, try to give it some inputs, check the outputs, and decide if the system is working correctly or not. And we'll see how this is applied also to software. So why do we want to do this anyway? So, well, testability improves other qualities of the system, as well as delivery time and cost. So other qualities is maintainability, for example, or bug prevention. Or another view, this is quoting Dan North, it says that the goal of testing is to increase confidence for stakeholders through evidence. So basically is trying to assess if the system is fit for purpose or not, okay? However, with testing, there are some issues. I don't know, who knows this guy? Yeah, you are Dutch, you know this guy. Eberhardt Dijkstra. So he was very much into formal proofs of software. He said, you know, testing shows the presence, not the absence of bugs. But then these other two guys, so this quote is attributed both to Yogi Berra and Albert Einstein, said, well, you know, Eberhardt, in theory, there is no difference between theory and practice, but in practice, there is. In fact, one of Boris Bezer, a very famous guy in the testing world, in this book said, the act of designing tests is one of the best bug preventers known. The thinking that must be done to create a useful test can discover and eliminate bugs before they are coded, which is very interesting. This is well before TDD, test first, or, you know, these names were invented. And design thinking can discover and eliminate bugs at every stage in the creation of software, from conception to specification to design, coding, and the rest. And in fact, good tests help in preventing and fixing bugs. Yeah? Give us confidence that changes won't break existing functionality. So yeah, they can only prove the presence, not the absence of bugs. But if we have a good suite of tests, we have a kind of statistical certainty that things will go well. They scale much better than formal methods and formal inspections. This is very important, okay? Who knows what formal inspections are? I'm not talking about vanilla code reviews that are, as they are done nowadays. It's basically people spending a lot of time analyzing the code and deciding that everything will be fine. They were invented in the 70s, when a big piece of software would have been, you know, the equivalent of 1,000 lines of code, okay? In my team nowadays, we write 1,000 lines of code per day, probably. So doing this wouldn't scale. So yeah, tests maybe cannot prove much, but using them correctly can help us a lot. And most can be automated, which is a fundamental thing. And then let's see a bit more about automated and manual tests. So automated tests are mainly for maintenance, evolution, and defect prevention. So every time somebody tells me that writing tests, automated tests, is a waste of time if the software is correct, they are not understanding the purpose of automation. Okay? The purpose of automation is not to prove you that the current version of the software works, is actually to help you to produce the next version of the software without introducing new bugs in it. Is it clear? Then there are the manual ones. So the manual test should be to do some other things. So mostly finding bugs. So I'm talking here, manual test is not follow the script blindly, as many companies seem to think, but is about exploratory testing. It's about humans using their brains to try to poke the system and see if they can find issues with it. Okay, so it's a different thing. And also for usability testing, there are some things that deciding that a system is intuitive to use, you need humans to use it and see how easy it is for them to perform tasks. We are not still able yet to do this with machines, or not in full. Yeah? So that is the usability testing, is self-operating napkin. I don't know if you, it looks pretty much like lots of software applications I've seen in practice, overcomplicated for what they do. And then there is the design aspect, which is important here. So this is Grady Butch, and he said that every software-intensive system has an architecture. In some cases, that architecture is intentional, while in others, it is accidental. Okay, so the big ball of mud, the spaghetti code you have, has an architecture. Okay, maybe it's not intentional. But the other interesting bit is the architecture of a system is the naming of the most significant design decisions that shape a system. Where we measure significant by cost of change and by impact upon use. Okay, so let's see what these things may usually are. So let's talk about the qualities. It's generally the qualities of the system, which I will list in a few moments. So usually qualities have to be baked in because they cannot easily be retrofitted, as you can see from the picture. Yeah, making that thing a Ferrari is kind of complicated. Yeah. And often are the main architectural drivers, are the things that will be difficult to change later. Yeah? So some examples of external qualities, for example, scalability. When they say a system has to be scalable, which in itself is a very generic term because it depends on what you want to scale, but this is for another talk. Yeah? It's just, I want here to stop at the intuitive understanding of this. Could be, maybe we can talk in front of a whiskey about this in more detail, or throughput, or latency, or usability. These kind of things, yeah, cannot usually be retrofitted, or even security, yeah, which is one that is often forgotten. They cannot easily be retrofitted. Usually, if you want a system to be scalable in your design, you hack something, and then you say, okay, now make it scalable. How many of you have been in that situation? I've been there, and it's not pretty. Okay. And then there are the internal qualities as well. So they are not usually directly visible from the users, but they impact what the users get. Yeah? Maintainability, which obviously, if the system is maintainable, will allow you to deliver new functionality faster or fix bugs in a more easy, faster and things like this. Supportability, this means how easy it is to support the system in production. What kind of information gives the ops guys to decide what to do if something doesn't go as well as it should. Yeah? Diagnosability, how easy it is to understand what went wrong from what the system tells you. Yeah? When there is a bug discovered, how easy it is from seeing the logs or the outputs to decide, I know where it is, it's in this part of the system. These kind of qualities are important. And testability, of course, is the subject of this talk. Now, let's talk a bit about costs because when we talk about testing, I always have these interesting conversations of we cannot write automated tests because we have no time is costly. Yeah, it's expensive because obviously it's lots of more code you write, for automation or for testing, and more code requires more time, and more time means more money. But the thing is, the total cost of the system is basically cost to develop. That is, let's say, from when you start to the first release, yeah, plus the cost to maintain, because after the first release is kind of maintenance. What you do is evolution, yeah. The cost of maintenance, there is a cost of understanding, yeah. So I worked for many years as a contractor. I landed on random projects. Is do something with the system, look at the code, and the first thought is, what the hell this thing does? How easy it is to understand that. There is the cost of changing it. Cost of changing means, how much time do I need to spend to fix this and to do all the related operations to actually put the change in production. The cost to test it, which includes the cost of writing the test, plus the cost of spend, the time you spend in testing, and the cost to deploy the system as well. Yeah. The thing is, all these costs are related. So you cannot say, we don't do testing, so we'll save money. Because if you don't have proper automated tests, the cost of understanding will go up, for example, yeah? And the cost to change will go up a lot. I worked in systems where a simple change would take 6 months. a tiny, simple change, simply because there were no automated tests and the code was difficult to understand. Okay, so all these costs are actually related. So just saying remove one of them will save money is not the way things work. You remove one of them, some of the others will go up. Yeah. And then there is the other thing that usually the maintenance, so the evolution and maintenance of software takes 60% of the cost of during the entire software lifetime. So you actually want to have the thing to be maintainable. Yeah? Otherwise, it's going to be difficult to keep it in operation. I worked on many legacy systems that were so difficult to operate that the company decided to write the new version. And usually that is an interesting decision because then you keep maintaining the old one and the new one tries to catch up at all times. And so you end up paying more for having a system that in practice doesn't work. Yeah? And in fact, according to Capers-Jones, now I'll give you this data as anecdotal because Capers-Jones doesn't really publish his methodology on how he gets the information. But according to what he said, in US in 2011, so he measures software in not function points. So, and they said, you see, the cost per function point in US in 2011 was, the average was $2,000 and was 1,000 bill and 1,000 maintenance and support for 5 years. This was the average. But in situations where there were effective defect prevention and removal techniques, yeah, the total cost 1,200, so 800 less, yeah, per function point. There was 700 to build, you see, less expensive, and 500 for maintenance and support. Okay, so from a cost perspective, doing a good job actually saves you money. But what about time? This comes from Steve McConnell. Who knows Steve McConnell in the room? Okay, so here what it says is, this is, how long it takes to do something, the development time. This is the percentage of defects removed prior to release. So the interesting bit is that most organizations are here. So it takes quite a bit of time and there is plenty of defects, yeah? The organizations that are actually here, in the 95%, go very fast. Over this point goes, is exponential because intuitively, even if there are the few defects that remain, can be very difficult to find and so very expensive. But for most situations, this is perfectly good. You go here only if there are human lives at stake. Yeah, you're sending a rocket to the moon. You probably want to spend a lot of money just to find some major issues. Yeah, you don't want people to die, or not usually at least. Okay. But then how do we do this? So we say, okay, it's all nice and good, but how do we proceed with designing for testability? Well, first of all, let's introduce two concepts. When we talk about testability, there are two measures that are called observability and controllability. So observability is how easy it is to infer the internal state of the system from external outputs. Yeah. So you're testing the system, you look at it and say, okay, I understand that now is is performing well or is not. Yeah. Controllability is how easy basically to tweak the system so it does what you want it to do. So when you perform a test, you want to put the system in a specific state. Yeah. So when you give it the inputs and get the outputs, you know what to expect. Yeah. This is the controllability thing. And how do we do that in typical tests? So we usually use tests that take 4 phases. So the first one is setup. This is basically is a controllability step. Yeah, you set up the system in a known state. Yeah, how easy it is to do that gives you controllability. Exercise, that means you give the inputs. Basically, you use the functionality you are testing. Verify, check that what has happened is what you expected. This is the observability bit. Yeah, you look at the system and say, yeah, okay, looks good, or something is wrong. And then the teardown is clean up the environment so you can run another test. Yeah, in automated tests is a very typical thing to do. In manual tests, it depends. Sometimes people try things one after the other. And now let's see how actually designing the system influences your ability to have something that is testable. Well, if you go with big upfront design, this is a famous architect I work with, was not very good, especially after the crystal ball broke. But the thing is, quoting again the same book, that big design up front for testability is a problem. Because basically it's difficult to decide where to put how to design your control points to observe the system and to control it. Yeah? Because when you have the big design up front, you are not experimenting with the system, so you don't know, you only guess where you may need all these things. Yeah? So it makes it quite difficult. And in fact, I've never seen a system that was designed up front that was actually testable in a reasonable way. Generally was just run the whole thing and compare to an existing database of answers or something like this. Then there is the no upfront design, which sometimes brings to cowboy coders, but there are some positives. So it actually works if the design emerges by coding and refactoring. Yeah? If you do TDD properly, if you are able to do that. Can be quite effective. I've done this, but requires a higher level of expertise. Put it in other ways. So, for example, doing TDD, who does test-driven development in this room? And with test-driven development, I mean, you really drive the development with the tests. Yeah? How easy it is to learn this skill? My experience with working with teams is that it's actually quite hard because you have to know about design and you have to know about lots of things, and it's not that easy. And it's actually challenging for teams that are beyond 3-4 people, because when the team grows, you need everybody on the same page. You know, you cannot really, if you have a team of 10 people, or if you have, in some projects I've seen 100 teams of 10 people, you know, you probably need some design there, so everybody pulls in the same direction. Yeah. So it doesn't work for large systems. The approach that generally is in between, that tend to work for systems of all sizes, is a rough upfront design that helps in baking quality in. So basically you have a high-level view of the system. You don't design everything in detail. Probably you experiment and prototype a bit to check that you can actually deliver on the main qualities and to decide what design to have to satisfy the main qualities you want. So if you say, we want a system that can be scalable or can be available, you know, with 5 nines availability, how do we provide that? Maybe spinning up new servers. Okay, so you have to design in a way so that when you spin up new servers, everything works. You know, the state is propagated correctly and all the things, yeah? Can be quite effective. It can scale to bigger teams, yeah? And of course, the design changes and evolves as necessary. So rough upfront design doesn't mean that once you come with a high-level design, you will keep it like that. But if the context around the system changes or your understanding changes, you may want to change the design as well, okay? And this helps with testability, because going in this way, as you design and you test, yeah, you can create your control and observation points more easily. Yeah, you don't need to have everything there from the very beginning. And in fact, to do this, to design for testability incrementally, it's very useful to use a working skeleton. Who knows what it is? It's basically implementing a system end-to-end in thin slices. Okay, so let's say that you have a random system like this. This is a kind of, this is what we think we want at the end, as of, you know, as of today. But then we'll start with a piece of functionality end-to-end. So from the UI, database, and back, a thin slice. Doing this, you can start writing the test for that thin slice and evolve the design, all the details of the design accordingly, making sure that you can test everything you need at all levels. Yeah? Does it make sense? And I put this slide because it's interesting. Now, you know, the old test first, TDD, seem to be very recent, but this is a paper from 1969 that is the report from the first software engineering conference in 1968 in Garmisch-Partenkirchen in Germany, where they invented the software engineering term, by the way. And they talk about testing interlaced with design. Okay, I won't read the whole quote, but it's basically do the two things at the same time, because it's the only way to test your system in a reasonable way. So it's nothing new, really. Okay, it's been there for a long time, yeah? Almost 50 years, but sometimes we forget the past. Which actually works really nicely with, I put here test first because even if you don't do full TDD, even if you do a bit of design, it's always better before writing any code to write your tests first. Because even if it is not full TDD, your tests will help you design a better system. Because if you do this, you'll say, okay, this is the way I want to test it. I need to connect to the database from here. Okay, I need to add something so I'll be able to do that. Yeah, you'll have this feedback back and forth, and at all levels. Yeah, this is at the acceptance system level or more class unit testing level. And then there is the other aspect. We talk about qualities. They need to be designed. They also need to be quantified. The system has to be fast. Typical request I have. The thing is define fast. Yeah, put numbers. Yeah, you really need to put some numbers there that I can use so I know what I'm aiming at. Wouter mentioned this approach in his talk before. Yeah, and it's always possible. Actually, if you ask Tom Gilb, he will show you how to measure love in quantifiable terms. Yeah. So this is very important because I still see many things that say the system has to be scalable. What do you mean with this? We need to increase the number of users. How many users will be the peak load? Yeah. What kind of numbers we need to put there so we'll be able to say, yeah, we know that now the system works as we want. Yeah. The other thing we do when we design systems for testability, we deal with something that Michael Feathers calls seams. A seam is a place where you can alter the behavior in your program without editing in that place. I'll show you a few examples. And then there is an enabling point. Every seam has an enabling point, a place where you can make a decision to use one behavior or another. So, and he gives a few examples. So object seams, link seams, preprocessing seams, test hooks, there are others, but I'll show you what I mean. So an object seam. Now, don't spend too much time trying to understand the whole code, but look at this event producer thing. Here and here is used. So this is the seam, yeah, where I have the behavior. And there, the constructor has the enabling point. This is where I can decide which behavior to pass there, yeah, which implementation of the interface. Is it clear? Yeah. Another example of a link seam, if we keep talking Java, yeah, this is the seam, and this is basically defined in a different jar. Yeah, if you have a situation where you have something, you know, replace a jar with another with the implementation of this particular class, that would become a link seam. In C++, they are more commonly used, you know, linked to a different dynamic library, for example. The test hook among these ones is the most interesting to me because a test hook is code that is used to configure the system to behave differently during testing. How many of you have seen test hooks in practice? How many of you like test hooks? I've seen you too now. Now, so a test hook is something along these lines, yeah? If I'm in testing, maybe with some property or something, do something, otherwise do something else. Yeah? You can't imagine how many bugs this thing caused in the systems I worked. Yeah? Landing as a contractor, looking at the system, working, say, why when I test this works and when it runs in the environment it doesn't? Simply because the code was completely different. This is why. Or sometimes I've seen the system run in production with the testing enabled and doing some really dodgy stuff. Yeah? So the thing with test hooks is that they actually change the system in a way that you don't want it to change. So testing is about verifying the behavior of a system. Yeah? So if it behaves differently when it is under test, you are not really performing a test that makes much sense. Yeah? So in fact, test hooks, you know, are dangerous because violate the principle that is about testing the system. But sometimes, in very special situations, can be a stepping stone in making some legacy code testable. Okay? Now, I won't go into the details. We can talk about details later on after the talk outside. But there are situations where this can be the first step of a series of actions, but it has to be taken with extreme care because the potential to destroy the system in production is high. Yeah? And then why all this seams discussion is interesting. So how many of you know what mocks are? Fakes, stubs, so everybody. So basically, when we use mock objects, spies, stubs in our test, what we are doing is actually creating new objects to new behaviors to put, pass to our enabling points and test the system, yeah? And they will come in I'll mention them a bit later now. And then there is another aspect. There are APIs for testing. So what are they? APIs that are to query or change the state of the system. Think about, often we use them in system testing. Yeah, we are outside, the system is deployed in a production-like environment, but we know we want to be able to do something with it, set some state, set some state or check what is going on, yeah? So things like also to query or change the configuration of the system itself, logs and notifications. Also logs could be APIs for testing. And these kind of things often become support APIs. Yeah, imagine things that say, they put a queue in your system in a specific state, add data to a queue. You have this functionality initially for testing purposes only, but then in support, it can become useful in support because you want to fix some bug, and then you are able to put a new event in the queue, stuff like this, yeah? And here is a graphical example. So let's say you have your system in production. The entry points in green are for the standard published APIs. The other in black are the entry points for testing. So often you end up in this situation. Your test runtime will have, during the test, to access a database directly, to access maybe some of the public functionality, but also some other private things to test and observe what is going on. Yeah. And some examples, notifications of asynchronous events, or timers to check performance parameters. How many of you have tried to, for example, test performances in terms of how fast the system is or how big the throughput is? Often we need to add things there so we can actually check or say, okay, it's performing as we want, yeah? To monitor asynchronous queues, again, is the queue receiving the data we are supposed to send there or not, yeah? Stuff like this. And when we talk also about testability, there is something we really need to keep in mind that Java programmers are especially fond of. That is, beware of frameworks. Really careful with frameworks because they can be very useful, but they can impair testability. When you have a framework has some assumptions about the surrounding context, okay? And sometimes those assumptions go against what you want to do with your testing. Yeah, I've had some interesting experiences with Hibernate, Spring, and some other Java frameworks that really got in the way of doing sensible stuff. So if you choose to use a framework, be careful about how you want to use it. Yeah, it has to be very clear what the impact is. And so, in short, a big part of designing a software system for testability is deciding where to put the SIMs and their enabling points and to create the necessary APIs for testing. So when you think about design for testability, what you're actually trying to do is, okay, where do I want to act in the system? Where is it convenient to put these points so I can see what's going on, yeah? But this is not all. There are some other things we seem not to talk that often when we talk about testing, that is ease of building the system. If it is difficult to compile the thing, yeah, you will run the tests less often because you cannot be bothered. Yeah, maybe there will be some small level tests, but what about end-to-end or some integration tests? Requires lots of manual procedure, lots of work. You know what? I'll pass. Data loading and setup procedures. How do you load the data, for example, in the database to create users or to put their information that you can use to perform your tests? Think automated tests, but think also exploratory testing. I want to do something and I want the system to have some users already set up, some administrators, but I don't want to click my way through that. Yeah, I want to have something that helps me and speeds that up. Yeah, how easy it is to do this? Yeah, if it is easy, probably your system is testable. If it is difficult, well, something is wrong. Startup and shutdown procedures as well. Yeah, how easy it is to start up and shut down the system and put it in a known state. Deployability, how easy it is to deploy it in a particular environment. I'll talk about deployability a bit more in a minute. Configurability, the same. So let's have a look at deployability. So is how reliably and easily can the system be deployed in a particular environment? Yeah. Does it require some special hardware configuration? I work in systems that to be deployed, they really need special hardware. And these, if you have to test that kind of system, basically means there is a added friction to do that. Does it require some special OS configuration? you know. Or does it require special directory structure? Are there many parts to deploy? For example, microservices. This seems to be something that many teams that want to use microservices ignore. Yeah? If there are many things to deploy, it will be more difficult to test. Yeah? It's a balance there. You really need to know why you want to use a particular architecture for that. A configurability is similar, but how easily can paths, databases, and other external resources be configured? I worked on a system once that the test data that was written in C++, and the databases were hard-coded in C++ macros. Okay, so it could be tested only on a specific test database, could be run only in a specific production database. Now, you can imagine how easy it was to test that system if there were 2 people that needed to run tests. Yeah. So external resources hard-coded. Are paths fixed? Things like we install on Windows, C program files, blah, blah, blah. Then maybe you want to have 2 installations of the same system to check things, and you can't because the path is hard-coded. Yeah? Can resources can be configured at compile time or runtime? Similar thing. But also too few or too many, or the wrong options could be a problem. Once I worked on a system that had configuration in XML file, but there was a forest of XML files, a file that pointed to a file that pointed to a file, to the point that basically the system had a life of its own and worked by magic. We were really unsure about how to do stuff with that. Yeah. And also, when we think about tests and runtimes, how do we do that? So tests and runtimes, we can have them in separate runtimes. Dependencies are set up via configuration and may rely more on special APIs for testing. So a situation where, let's say that we have an auction application. This runs on the client side. There is a server, and the test runtime is external and has to connect to both. Okay, so each of these applications runs in its own computer, so they don't share surrounding context. They have to communicate via APIs. This is a way of testing. Yeah? Sometimes we deploy stuff in production and then run the runtime. But there is another way as well. Sometimes it's convenient to have them in the same runtime. So allows the use of dependency injection at the language level. So something like this. Yeah. So the test runtime actually starts up the server, the client, and does stuff with it. Or this example is from the Goose book. Do you know who knows the Goose book? Growing Object-Oriented Software Guided by Tests. Okay, so I think it's one of the best books about TDD, but the example there is about test assisted in the same runtime. So they have a fake auction server and an application runner that are started by the test, yeah, itself. So the test runner starts this and this, which is extremely convenient if you use TDD or test first, because you can run a whole load of functional tests. I'm not talking about performance tests in which you need to have the separate runtimes, but a whole load of functional tests of various kinds very quickly also in your IDE. Yeah? But the same runtime comes at a price. And the price is the global application state should not spill over. Yeah? You have the server and the app running the same, started with a new in your test. Yeah? And if they use singletons or global variables, the state of the server or the client can spill over. Yeah? And this can cause really interesting situations. And frameworks must play nicely as well. Some frameworks sometimes have assumptions about the global state of the application. Okay? So if we want to talk later about this, I just tell you that I would suggest to avoid singletons always at all costs, no exception whatsoever. I don't care what you think. We can talk about that later. Okay? And also, there are other aspects. That is, the tests need to be reasonably simple to create. So this is why testability is important. If the tests are difficult to create, not many people will create them. Yeah. Provide feedback at the right granularity level for observability and controllability, and has to be easy and fast to run. Basically, otherwise, nobody will run them. Yeah. And this is the test automation pyramid. Basically, what it says is, I'll show you also, from the lowest to the highest in terms of maintainability, execution speed, and automation level. So these are the fastest and more maintainable. And the higher you go, the more difficult it will be to maintain, because it will involve more of the system, and the slower they will go. And generally, this means you want to have lots of these, less of these for up to a few manual ones. Yeah. So the point is, if you want the system to be testable and the test to run, you want most tests to be very, very simple to run and easy to run. Yeah. Which goes to the system test. Other conversation people that say unit tests are rubbish. We only do system tests because blah blah blah. Well, it can be quite complicated to set up and run, especially for distributed systems. And I've worked on lots of distributed systems. It can be very slow. With giving also the feedback loop will be very long, and so again you will run them less often because of this. May be very difficult or even impossible to run on a developer's machine sometimes. Yeah. Don't scale well compared to other kinds of automated tests. The more you add, the slower you'll go, and even if you parallelize them, you will hit a point in which you cannot do that. So you'll have to choose which ones you want at some point. Are very unhelpful in pinpointing the hiding places for bugs. Because it's the old system, yeah, the test breaks, where is it broken now? Where is the point? Yeah, you need to isolate that. And their coarse grained nature makes them unsuitable for checking that a single class component, class function, does what it's supposed to. And I've seen these in systems that had no tests. I've seen developers doing a change in a class and run the whole thing to see if the class worked well. But really, they couldn't even know if the class was used at all. Yeah. And can be extremely difficult to use with distributed teams. Now, I tell you, from the point of view of having been involved in projects with tens or 100 teams, okay, can be, and in one project in particular, they had like 800 developers in 70 or 80 teams. The mandate was to use system test only, was a single product, okay, was not microservices or anything like this. And waiting for system tests meant that whoever was ready first had to wait for others. So the test of the system could happen, or of any part of the system could happen months after the code was written. Now, I won't tell you how many bugs they had. You can imagine that. Yeah. And in fact, when you have many teams, usually when you have several teams, the system tends to mirror the way the teams are distributed. What happens is that your best bet to have a system testable is that you write it for testability so you can actually mock the dependencies here. You want to have a level of system testing, but you want to have agreed interface and test in isolation. This is the best way to go fast with a reasonably tested system. And some final remarks, because I think I'm almost done with time. So testability adds complexity in some dimensions. You write tests, you have to think about the design in a different way. You have to think about the dependency injections on the SIMs, the enabling points and all this stuff, but simplicity in others, yeah? Because it will be easier to make a change. Yeah, if you have a suite of tests that run and is quick, you try your stuff very quickly, have a short feedback loop and simplifies your work. The tests need to be maintained, yeah? This is added work. But it's cheaper maintaining the test than running the application manually to smoke test changes all the time. Yeah. And I think, sorry, what did I? Okay. And then a few takeaways. Testability is actually a very important system quality, so you really need to think about this. Saying you cannot test because you don't have time is just the wrong thing to say. It's just wrong. You'll pay a price later. To be tested, the system has to be designed to be tested, because if you don't think about all the enabling points and the SIMs and the APIs to let the system do things, what happens is you'll have a block of stuff, and your only way to test will be run the entire thing and check your results compared to whatever production database of the day you've got. Many investment bank systems are tested in that way. Yeah, and people actually give investment banks money to manage. So, it's kind of interesting. And actually, having well-chosen tests allows us to create quality system faster and cheaper. So the typical metaphor I give for speed is that when people don't write tests and hack code, they have the feeling of speed. Okay, the example is with the Italian cars. The Fiat 500 from the 60s or 70s was small family car. Top speed, if you really pushed hard, was about 100, 105 kilometers an hour. But when it was already 78, it would vibrate, lots of noise, move, and you felt, whoa, I'm running fast. And then you get the Ferrari, okay? You go Ferrari, 100 kilometers an hour, so, Yeah. 200 still feels like a stroll. You are going much faster, but you don't have this feeling of speed at all. It's just because it's a better car for that, okay? So sometimes we develop systems in this way. We want to feel busy, doing stuff, and we feel like we are making progress, when in fact, all we are doing is lots of movement, lots of noise without any real progress, yeah? And I believe that tests first at all levels help. Thank you.